I'm Matt McEwen, a PhD student at the University of California, Santa Barbara, and a researcher with the Google Quantum Hardware team. And today I'm going to be telling you about our work identifying catastrophic error bursts from high-energy radiation in our large qubit arrays. So first, for a bit of background. For practical quantum computation, we need a lot more resources than we currently have. For the standard superconducting qubit architecture, that basically demands that we take advantage of quantum error correction. And that means that we need millions of high-fidelity qubits working together, not only a lot more, but also better than we currently have. And bridging that gap is the big challenge facing our field. So quantum error correction of this kind involves repeated stabilizer measurements, which give you information as to what errors have occurred. The success of your quantum error correction comes down to whether you're able to match up the detections you're given correctly. Now, codes like this are known to have robust thresholds to independent errors, meaning that if the density of errors is low enough, the matching will work quite well. But while codes can handle a small amount of correlated errors, really dense regions of many errors caused together will derail the correction process, producing logical errors and causing our computation to fail. So in short, high-density bursts of errors are not correctable. Meanwhile, high-energy radiation is ubiquitous. It's produced in small amounts in the materials we use for our buildings, for our lab infrastructure, and in fabricating our devices. It comes down from the sky in the form of cosmic rays, and it rises up from the ground in the form of radon gas and its daughter isotopes. Now, these are well-known sources of error in the high-energy particle and astronomical detector community already. But it's going to be important for our field to study and understand what these high-energy particles do in our devices as well. So for this talk, I'm going to first go through the basic story of what happens when one of these particles interacts with our chip. And I'll then address how we found and measured these impact events and what they mean for our device. And then finally, I'll give some thoughts about how we're planning to handle these impacts going forward. So for the story of an impact event, when a particle passes through the chip, it deposits a lot of energy in the substrate where it impacts. Now, there's some rich physics in the initial stages of the impact chain that I'm going to gloss over, depending on the kind of particle that arrives. But generally, the energy is distributed between free charges and phonons. And I'm going to focus on the phonon part of the chain from here on out, because something like 80% of the energy ends up in phonons, and also because they're what's most important for the resulting error in our device. So very quickly, the deposited energy scatters into high-energy primary phonons. Now, the primary phonons do down-convert in the substrate to near the Debye energy, but in silicon, that's still 2 orders of magnitude above the superconducting gap for aluminum. And that means when the primary phonons hit the superconducting layer, they're rapidly absorbed, breaking up superconducting Cooper pairs and producing quasiparticles. Now, these quasiparticles have a lot of energy, and so they scatter out secondary phonons as they cool down towards the superconducting gap. These lower energy secondary phonons have a lower absorption rate, which allows them to bounce across the whole chip very quickly, spreading energy rapidly throughout the device. So these early stages would lead us to expect to see a hotspot of initial quasiparticles in addition to elevated levels spread out throughout the device. The next relevant timescale is the recombination of quasiparticles near the superconducting gap, which produces tertiary phonons. At the high densities near the initial hotspot, this can happen on a timescale of around 100 microseconds, but further away it can extend out to something more like a millisecond. So this should lead us to expect that as we observe the event for longer times, we should see that initial hotspot spreading out. Now, the key reason we care about the production of quasiparticles over the chip is an effect called quasiparticle poisoning. So quasiparticles are abusively non-superconducting electrons, and if they tunnel across the Josephson junction along with the qubit current, they're capable of stealing the qubit energy and producing a decay error. So this is a very well understood source of error for superconducting qubits, and it's proportional to the density of quasiparticles near the junction. So typically, we keep the background level of quasiparticles very low to prevent this error source affecting the qubits, through keeping the device nice and cold, and also through careful filtering of our qubit control lines. However, given the amount of energy deposited on the device during the impact event, we should expect to see much higher quasiparticle densities, and so greatly elevated levels of decay error. Now, if all the qubits are producing decay errors at the same time due to one of these events, we're going to see exactly the kind of high-density error burst that would be problematic for quantum error correction. So, from this impact chain, we should expect 2 clear signatures. First is a localized hotspot, which subsequently spreads out, and the second is the qubit seeing a severe T1 decay error from quasiparticle poisoning. So with those predictions in mind, we can now design an experiment to go looking for these events. Because we're worried about a highly correlated signal, we can take advantage of that to run our experiment. So the underlying experiment is very simple. It's just taking a single data point T1 measurement on a single qubit. So that means initializing it into the one state, waiting a little bit, and then measuring and seeing if it's had a decay error. We then tile this experiment over a large number of qubits, so 26 in my case, and repeat it very rapidly, allowing us good time resolution and building statistics. The majority of the work in this project is actually hidden here, convincing all the qubits to work together, where I'm taking advantage of the great work done by the entire quantum hardware team over recent years in fabricating and operating these devices. So the circuit we're repeating here is also very similar to the quantum error correction experiment cycle, so the absolute error rates we find will give us some insight into the code performance directly. When the device is operating, there's going to be sort of a base rate of individual qubit errors, which are set by known quantities like the qubits T1s, the idle time, and the readout fidelities. Importantly, those errors are going to be essentially independent. When an impact occurs, the amount of energy involved is likely to cause a big problem, where a large number of qubits will all have errors in a time-correlated way, and that strong correlation is the signal that we're looking for. So if we run about a 30-second experiment, we can find something that looks like this. First, there is a baseline of around 4 errors per round here, and there's some noise around that. But at some point, something happens that basically makes all of the qubits freak out at once. The average number of decays jumps up to 24 qubits decaying in each measurement cycle, which basically corresponds to the device not working. We should immediately notice also that the relaxation back to baseline here is horribly long, about 25 milliseconds exponential decay constant for this event. This is the result of a trade-off in our device packaging for a clean EM environment, but it means that our chip is thermalizing very slowly after an impact. Regardless, just based on peak size, this is not an event that would be survivable for a quantum error correction experiment. Now, if we take a lot of data sets like this, these events are actually quite easy to find. And this lets us look at their time distribution. So specifically plotted here is the time between pairs of events found in the same data set. And the red line is the expectation for a Poisson process with an average rate of one event every 10 seconds. You can see visually it matches pretty well. And it's also worth explicitly acknowledging that this event rate scales with device size. So making larger chips with more qubits means these events will start to happen even more. So now we can take advantage of the work we've done on Sycamore on fast cycling, readout, and reset to take data with a very fine time resolution. This lets us study the sort of rising edge of the events, the initial impact and spread. So here, the time between data points is only 3 microseconds. This is the same event shown on 2 different timescales, zooming in on the start of the event on the left and zooming out on the right. And we can see 3 distinct timescales, which fit pretty well with our understanding of the energy cascade. There's an almost immediate jump from the baseline level of error up to about 10 errors here in about 10 microseconds. And that's followed by a kind of saturation, where the error number continues to rise for about another 1 millisecond, slowing down as it gets towards the peak. And then finally, the error is dominated by the familiar 25 millisecond relaxation back to baseline. So this is already a nice sign that we have some good understanding of the dynamics of an event, but more interesting is the spatial behavior. So you can see here that there's an immediately obvious hotspot. And that localization is a great sign that we have found an impact event. Each event we find has a similar hotspot that varies in location, sometimes on the qubit patch and sometimes off. And so this sort of confirms our initial expectation, our first prediction of a localized hotspot. So here are some more of these impacts. And again, you can see the clear localization in each one. So on the left, we've got a large impact on the right-hand side of the patch. In the middle, we've got a relatively large hit on the other side of the device, which seems to happen just off the patch and wash in. And on the right, we've got what looks like a smaller event, but actually just seems to happen further away from the patch, showing that error can spread over a really significant distance and still produce large amounts of error. So now that we've confirmed our first prediction of localized impact, we can turn to the second, which was a severe T1 decay error mechanism. We can use the rapid nature of our experiment to interlace different experiments so we can perform comparisons on the behavior of a single event. So as an example here, we can interlace experiments that initialize the qubit in 0 and 1 and look for an asymmetry in the qubit error. Decay errors should only really affect the experiment where we've initialized into 1. So because our qubits have a decay error as the dominant error mechanism, the baseline decay errors already are quite a bit higher than the baseline for excitation errors. But during an event, you can see that the decay errors jump up like we've seen before, but the qubit excitation behavior doesn't change at all, staying very low throughout. So this is a great sign we are dealing with a T1 error mechanism like quasiparticle poisoning over some kind of other error mechanism like readout failure or photon-assisted quasiparticle tunneling, where you'd expect a sort of non-trivial signal in the excitation experiment as well as decay. More complexly, we can interlace different idling time experiments to look for the scaling of the error source versus time. The quasiparticle poisoning hypothesis would predict a strictly exponential scaling of the amount of error versus idling time for a single event. So this data conveniently lets us extract an average T1 over the device at the peak. For this relatively large event, for example, we did indeed find that exponential scaling, and we extracted an average T1 over the device at the peak of 0.7 microseconds. That's come down from sort of 15 microseconds usually for this device, which is a really severe additional error. Using this T1, we can then back out the sort of quasi-particle densities necessary to produce that error in the initial hotspot, and we get something sort of 4 orders of magnitude worse than our expected baseline. This also matches really well with what we'd expect for the amount of energy deposited by a sort of just above average impact, given the cascade process we discussed earlier. So this is a sort of large but not unusual impact event. This also confirms for us that we are far from the weakly correlated limit that might be acceptable for quantum error correction. A T1 on the order of the quantum error correction cycle time would immediately sink a quantum error corrected qubit. So with our new understanding of these events, the next obvious question to ask is what we're going to do about them. So before we focus on mitigation, it's worth noting the short-term solution that in some ways we've all been using all along. These events are relatively rare on the timescale of a typical qubit lifetime, happening once every sort of 10 seconds for our devices and only lasting milliseconds. So unless we're running a single experiment that wants to last for longer than 10 seconds, it's possible to just look at the device performance in the regions between impacts. And actually, we can do this really easily because the impacts have a very distinctive shape and are very easy to identify. However, this strategy of post-selecting out the bad data only works first for events down to some cutoff size, meaning that small events still affect the experiment's performance. But more importantly, this doesn't scale. In the end, we want to run quantum error correction for hours or days on much larger devices, so we are certainly going to see an impact event, even if we used excellent shielding and really cut down on the events arriving at the chip. It's therefore going to be really important for us to mitigate these events in the device when they do happen. So mitigation strategies for high-energy radiation impacts have already been developed in similar systems, such as superconducting telescope detectors. So one option is adding low-gap absorbers on the backside of the device, which down-convert phonons to energies where they can no longer induce the harmful quasiparticles. So that was done on a telescope detector, and shown here, the effect is shown here on the top right. Another option involves changing the structure of the chip to include membranes that impede the propagation of phonons, preventing the error burst from spreading out so much. You can see that that strategy is shown in the bottom two plots. You can see that with these strategies, the chip-wide error bursts are significantly reduced down to a low-density spray of errors that you could hope quantum error correction would then be able to handle. More recent work on qubit devices has shown similar mitigation is really promising, such as a recent experiment shown here, where a normal metal phonon down converter was added to the backside of the chip to absorb hot phonons propagating in the device. With these strategies well within our ability to fabricate, the remaining challenge is really integrating these solutions into the large, complex quantum processors without decreasing coherence or gate performance. And that's a demanding future task for us. So in summary, we've identified impact events that induce severe correlated errors in our qubit arrays. And that's a significant challenge to our goal of achieving quantum error correction in a functional way. But we've developed sort of useful metrology tools, and we've understood the dynamics of these impact events. And so we have an important task ahead of us in developing techniques to mitigate these impact events in our arrays so that we can enable quantum error correction at scale. And with that, I'd like to thank the whole Google Quantum AI team for hosting me and providing all of the resources for this experiment. Cheers.